Hi, this is A.THASNI from Department of Computer Science and Design from SNS College of Technology. So today we are going to see about the topic called as transport layer from computer networks. In that we are going to see about the transport connection protocol flow control. So actually, how the flow control will be. For example, if you see in this slide, we have something called as fire hose and glass. When the fire hose, it will be a high bandwidth center with low capacity. So what the problem actually happens is which is the capacity mismatch. So where we have too much of data when we are sending to the receiver part, it should be a high bandwidth center, so we have to slow down to get all the data. We have to slow down. So there we are using the flow control. So there are two architectural approaches, whereas feedback versus rate. The feedback based is something we call it as the TCP method. The receiver sends the explicit signals like credits or acknowledgements to tell the sender it is ready for move. The sender transmits only after receiving the permission. Whereas in the rate based streaming method, the sender transmit a pre-negotiated fixed speed, then it assumes the receiver can keep up and there is no continuous feedback loop. So this is the main difference between these two approaches. Next, the evolution of feedback efficiency, like how it works. Like we are sending the frame one. So once we are sending the data to the sender, it will wait for a write time, where it is a waiting time for the idle time, where it is inefficient, like a link sits on the empty while waiting. Then once we receive the response, we are sending the acknowledgement to the frame 2. And in method B, we are approaching for the sliding window. Like in each frame, we are sending the acknowledgements pipeline, like one by one, it will be sending where it fills the bandwidth. So that without any interruption, the sender will receive the data for the till the end. Next, the anatomy of the window. The window is a portion of the buffer containing bytes that can be sent or received, like to the sender to the receiver. Actually, it breathes dynamically, where we have the buffer content. So once the sender send the acknowledgement and to the receiver, it is still we don't have any bandwidth for that. So we are storing the buffer content and it closes, and once it is done and it will send to the receiver. So the prime directive that don't shrink, which is a receiver should retract a promise that the right edge of the window can't move left forward. It has some like a formula, like a new acknowledgement number plus new rewind should be greater than the last acknowledgement number plus last rewind. So the danger of shrinking will be less, where the data will be sent to the illegal line. Next, we are negotiating the limits like through handshake. Handshake is nothing but from the client side, we are sending the data to sync to the receiver, and it allocates the buffer, how many it should retain, and then it will reallocate and it will send the acknowledgement plus sync to the receiver. So the acknowledgement will be expects 101 and the rewind will be 800 window size. So another one of the approaches silly window syndrome we call, like when overhead destroys throughput, where the header will be in the 40 bytes and it controls with 1 byte data. Where the ratio will be 40 is to 1, it is overheading, like metaphor, sending the massive shipping container to the transport a single apple. It causes a slow sender. Course, like it creates 1 byte at a time, and slow receiver it reads 1 byte at a time, not in a multitask. Solving SWS at the sender, which is called a Snaggle's algorithm. The main strategy is to accumulate the small data into larger segments. Send first it will send us a tiny piece immediately, and then it will start with the self-clocking efficiency, like fast network equal to small packets, and slow network will be in the big packets. Like then it will collect, it will wait and collect subsequent data in the buffer, then it will trigger to release, and it sends only when a full mess is ready, else it won't send. Like then it will send as a previous acknowledgement arise based on that. Again, it will trigger as release. Again, it will be sending to the self clocking. Like if it is a fast networking, it will be sent through small packets, and if it is a slow network, it will be sending through the big packets. Next algorithm is first we have seen from the sender side, and here it is from the receiver side. We call this Clark solution. The main strategy here used is stay silent until the meaningful space is available. So we don't advertise a 1 byte window, maintain a 0 window. Once the logic is done into 1 byte, then it will be going for the next byte. And next one is the trigger, and where the window will be updated, advertise only when space is greater than the MSS or buffer is 50% empty. Then only it will be released. The optimization we see here is delayed acknowledgement. Wait up to 500 milliseconds to group the updates. So it is a deductive, like we have the server sends 4000 bytes filling the fridge buffer completely. The fridge advertises like rewind of 0. The fridge application is very slow. It finally consumes 2 bytes data only. The fridge immediately sends an update to the receiver. This is how it will work. It's one of the puzzle game we can see. This is a mind map from TCP where it is going. We can see. This is the complete flow control mechanism of uh, transport layer where we have the stop and wait, and we have seen before. So the reference where we took, and you can refer the links like jigs for jigs and tutorial point. You can see more, get more information, and you can refer the book Behro's Person Data Communication and Info.